therefore, the final momentum of my 2 kilogram mass would be,
-2.
yes. Because these two have to add up to give me that.
What does the D stand for?
D is a unit I have made up because I don't feel like writing kilogram meters per second over and over again. So I call it a Descartes.
Oh.
Because Rene Descartes, the philosopher, also did some early work with momentum. Where Newton approached physics from a force point of view, Descartes was trying to do it from a momentum point of view. And it turned out they were related to each other. But, so that's a Descartes. There is no one word unit officially for momentum. So I can get away with that as long as I don't pick a letter that's already being used and as long as it's written down. As soon as I erase that, everything with a D in it is at that point wrong. Because since I'm making up the unit, I have to define it. All right, so let's figure out what the final velocity is here. So I know that this -2 is equal to the mass of the 2 kilogram object times the velocity of the 2 kilogram object. So -2 is equal to 2 V2 final. What is the final velocity of the 2 kilogram mass?
-1.
Units?
18%.
All right. The math problem, just solving for this, divide by 2, get -1. Questions on the momentum side of the problem? All right, let's take a look at the energy. What is the initial kinetic energy of the 2 kilogram mass? Initial kinetic energy of the 2 kilogram mass.
Joule.
Yes. It's a word. These black markers. There we go. I think that's the one. If I didn't draw the wrong one. Okay, good. That is for the 2 kilogram mass. The 4 kilogram initially. What is the initial moment, kinetic energy of the 4 kilogram mass? It would be. So the initial kinetic energy of the system is
27.
all right. Questions about how we got the 25, the 2, actually, questions about anything on the board at this point?
The 25 is just 1/2 FE squared, right?
Yes. As is the 2.
Okay.
All right. A2 final. What is the final kinetic energy of the 2 kilogram mass?
One.
And the final kinetic energy of the 4 kilogram mass? That's not gonna be the way it works. All right, anyway. The final kinetic energy of the 4 kilogram mass?
8.
So what is my final kinetic energy? All right, they didn't stick together, but there's still a loss in kinetic energy.
Okay, what was the math? Like, is it still like the 1.5 mv squared?
1/2 mv squared.
Is it still that?
Yes, kinetic energy 1/2 mv squared. Now it's
Did you
forever.
use V, did you use the final, are you just using the 2 for the
For
4 kilogram?
this one right here, okay, 1/2 mv squared. We're talking about the 4 kilogram mass, so that's 1/2 times 4 times, since we're talking about the final velocity or final speed, which was 2 meters per second. That's the math. 1/2 mass times speed squared. Jennifer, you look troubled.
I got it.
Okay. Yes, Elizabeth.
Why is that the final mass? So, wait, not the mass, the velocity.
Why is that? I gave that to you. I gave this startup and this part of the final and then that.
I see it now.
So
Okay.
for the 2 kilogram, it would be 1/2 times 2 times -1 or 1.
For over there, yes. Yep. 1/2 times the mass times the final speed squared.
Why is it 1? Where did that?
We got, that's what we first were trying to find, is that final velocity, that was,
Okay.
and because it's speed squared, that's why it's +1. Or even if you threw the negative in there, when you square it, the negative goes away. All right. Notice we lost kinetic energy. They didn't stick together, so it's not a perfect loss, it's just, there's some loss. So when you have a kinetic energy, when there's lots of kinetic energy, but they don't stick together, it's what I refer to as an imperfect collision. Let's do another one. time numbers that will work out the way I want them to. So 3 kilogram mass going to the right at 4 meters per second. A 1 kilogram mass going to the left at 6 meters per second. Afterwards, the 1 kilogram mass, so this is before and after. This is the 1 kilogram mass is going to the right at 9 meters per second. And the 3 kilogram mass we're trying to find that. Let's see if we can zip through this. Any questions on what's happening in the problem? All right, the initial momentum of the 3 kilogram mass,
12.
still using that over there. All right, the initial momentum of the 1 kilogram mass,
6.
my total initial momentum,
18.
what's my total final momentum?
8, 9. 9. Oh, sorry, 18.
18, yeah, there we go. Conservation momentum, what I had before, what I have afterwards. All right, what is the final momentum of the 1 kilogram mass?
9.
Therefore, what is the final momentum of the 3 kilogram mass?
9.
Why is this also 9?
8.
Yeah. Those two have to add up to that. So what is the final velocity of the 3 kilogram mass? About 9.
Oh, yes, sorry.
Something.
Why would
Oh,
the-
oh, there's a mistake up
I
there.
have a question.
Yes.
Why would the one initial be negative? Wouldn't that be -6?
That was the mistake, yeah, that's not 9, that's not 18. All right. Put some corrections in here. That would be -6. They are indeed opposite directions.
So then the P initial would be 6.
Yep, that's 6. So therefore, what is the final momentum of the 3 kilogram mass? In other words, 1 plus 9 gets you 6? -3. Yeah, that's working much better. So what is the final velocity of the 3 kilogram mass?
-1. -1.
-1. Because I know that's gonna be equal to the 3 kilogram mass times the final velocity of the 3 kilogram mass. So I get 3 is equal, well, the math problem, 3x equals -3, that's the math problem. Jennifer, do you have a question? Okay. All right, let's take a look at the energy. All right. What is the initial amount of kinetic energy here? Oh, you forgot to square.
Oh,
24. You square the 4, not the 6. So 24 joules. What about the initial kinetic energy of the 1 kilogram mass? total kinetic energy.
42 joules.
All right, let's take a look at afterwards. K3 final. 3 kilogram mass, 1 meter per second.
We 1.5.
And its final kinetic energy? So Mike, total final kinetic energy?
42 joules.
Hey, that's what we started with. So an example here where kinetic energy is conserved, this is known as a perfectly elastic collision. If we gain kinetic energy in a crash, what would that tell us? We smack two things together, we get more energy out than we started with. Assuming the masses don't change. There's been several movies about it. Pardon?
Well, I was gonna say atomic bomb.
Let's see, Fred McMurray was in it, in the original. Harry Anderson was in a remake. Robin Williams was in a remake. Something that when it collides has more kinetic energy than it started with. I don't know if you're just being shy or your education is sorely lacking. Flubber. I'm looking for looks of recognition from somebody. I got one person who recognizes what flubber is. What is flubber?
Yeah.
It's a material that, the first movie was The Absent-Minded Professor with Fred McMurray, then there was a sequel to that. But it's a material, flying rubber is what he called it, is that when it bounces it gains kinetic energy. So if I dropped it, it would bounce higher, and then it would just get faster and faster. It's, most physics textbooks call, if you gain kinetic energy, call it impossible.
The, final kinetic energy, the 40.5, how did you get that?
1/2 times the mass times the speed squared.
Oh, I had, okay, yeah, I had that backwards.
You forget the square or the half?
I had it backwards.
Oh.
I had the,
Yeah, that'll do it.
yeah.
All right. We're about to adjourn to the other room. We'll be doing a momentum lab. So that should bring some excitement there. And it is the most conceptual of all the labs that we do. So keep that in mind. And you're allowed a group hand in, if you wish. But we'll talk about that in more detail when we get down there. So prepare to rejoice.